Professor Yasemin is our next presenter. So let me introduce our next speaker for the keynote address, Professor Yasemin Ozkan-Aydin from the University of Notre, USA. Just a brief introduction of the speaker to the audience. Dr. Yasemin Ozkan-Aydin is Assistant Professor at the College of Engineering in the University of Notre Dame. She completed her PhD in Electrical and Electronics Engineering from the Middle East Technical University, Turkey in 2014. She was a postdoctoral fellow at Georgia Tech from 2016 to 2021. Her research lies at the intersection of robotics, biology, and computer science, specifically soft robotics, bioinspired design, and swarm robotics. She focuses on understanding the factors that play a key role in animals' locomotion and developing predictable, precise, and robust robotic systems that can move across unpredictable, complex terrains as skillfully as biological organisms. So this is a very interesting topic. May I request Professor Yasemin?
Thank you so much for the introduction. Let me share my screen. So, as you introduced, I'm new faculty at University of Notre Dame, and this is my new lab logo, Minero Lab, as a minimalist, naturally inspired robotics lab. So today I will talk about a bio-inspired approach to task-oriented legged swarms robots in a complex environment. But before start this topic, I want to introduce a little bit about, as you said, my research is the combination of the biology, physics, and robotics. In biology, you know that bio-inspired robotics and also robot-inspired biology. This is the reverse version. Robotics experiments inspired the biologists to do some understand some mechanisms in biology. So I'm working on both sides and robophysics and use the robots to understand the physics phenomena such as the walking in granular media is one of the hard topic in physics, the dynamics of the granular material. So you can use the robots to understand how these systems behave in granular media. And also in robotics, and I'm working on swarm robotics and hard soft robots that made by built by 3D printers or soft materials such as silicone. So, and also I want to a little bit introduce the terms, the biologically inspired, as you know, from material science to architecture, the computer science, or robotics, you can find a lot of examples from in literature. People use the biological ideas to design some, for example, the first one is on the left, is the high performance fiber silk. It's used in material science, is developed by using the idea from the caterpillar's silk. And also you can think about the algorithms that use the colony of the bee. This we call the artificial bee colony algorithm, how they communicate with each other, how they respond to environment, to the sensing, the distributed sensing in the environment. And also the last one is one of the example that use the gecko adhesive and on feet of the robot and that climb to the smooth surfaces using the directional adhesion of the feet. And the minimalist approach is this is one of the approach I used in my lab to build the systems. This is one of the example from the Suzumori and the lab. Is actually this is the guy is I really love his work. The pioneer of the soft robotics. So this is one of the examples what can be a complicated robot, how it's gonna look like. So there's a human-like robot, but there are a lot of muscles around. You can see as a pneumatically actuated muscles, and they connected to the pneumatic board on the back of the robot is covered with the sheet, but it's very complicated. You need to control each muscles individually to create some. You can see now there's on the back is a huge pneumatic board, control board. This is the idea. You can maybe work on that, but it's the idea in my lab is I use is the kind of similar to like on the right. This is one of the not this one. This is one of the examples that David Zorok is one of my friends. They use you can see that there's only one single motor on the front, but there's a creative design. It allows the robot to move in a lot of surfaces, such as the smooth surface, a rotary, and also this robot can also climb in a pipe without any control. Just with only one single motor is enough to do that. We call this as minimalist approach. It's because it try to use it as simple as the design is simple, but it used the minimum actuators or sensing to do for example, it's climbing in a tube without any sensing anything. And also, I'm also working on the Softheart robotic system. As you know, the traditional rigid robots is very good at in factory environments, such as the assembly of the things. They can do the things very frequently without any error, anything. But when they encourage this is the precise, predictable, fast. But if this is one of the example from DARPA challenge as a humanoid robotic challenge. When the robots, this rigid robots come to the real world, very simple tasks such as climbing stairs or open the door knob, they can't do that. Yeah, they mostly fail. So, for example, here it's trying to open the things, but it couldn't reach, but it's fell down. So a lot of error happens. But in this case, people start to, this is the area, actually it started maybe 30 to 40 years ago, but last 10 years is the more popular area. This is a robotics. It's a very low cost, safe, lightweight robotic systems. You can use the silicone to create them, such as inspired by, for example, this robot is inspired by octopus and is also used for the manipulators, the soap manipulators. This is one of the example. It just uses one single actuator. It's used air pneumatic actuation, and it can hold the objects safely without disturbing the environment. So I am working on this topic also. And these are now I'm switching to my research. I have been, as I said, I have been working on biological systems. These are the 3 example animals I worked during my postdoc life. The salamander that has 4-legged and it used the body undulation to move. Centipede, it has multiple legs and flexible body, and earthworm is completely soft body. It can burrow in soil. And these are the 3 example robots. The left one is the salamander robot. It's built by 3D printers. It's very rigid. It has 4 legs, and each leg actuated by simple servo motors, but all the things are rigid. And there's another robot, is the earthworm robot on the right. Is the completely soft. Just the connectors are the segments. There are 4 segments, and these are just connected with the rigid segments. But other than that, all the body are made by silicone, and you can use this robot in, for example, in pipe inspection. You can put this robot to bend its body easily, adapt its environment. And also the middle one is combines the hard and soft materials, the centipede robot. And my swarm robot is I will explain in the next slides. My swarm robot is inspired by this robotic system. Let me show the animal first. For example, this is the centipede. It's used, as I said, it has multiple legs, and it has a body undulation that goes from head to tail or tail to head, and it's coordinate its body and legs in smooth surfaces. This is like a snake. Undulation is one of the way to locomote. But in raw terrain, this is on the right, is one of the video I took in my PI's room. You can see that it has of course, the body is very flexible, but when the legs are hits the obstacle, you can see it bends to the back, and it's maybe passively or actively, but we try to understand what is the function of this one. So here I design a robot as using the minimalist approach, as I mentioned at the beginning. It has the segments. In this one is, for example, it has the 8 segments, and each segment has the 3 servo motors. The one for body undulation, and 2 for the legs are coupled, and 2 servo motors control the up and down and fore and aft motion of the leg servos. So this is the example how it's looked like. For example, if you move this robot, one of the legs to the up, its other one goes down. And if you turn to one of them left, the other one goes right. So and here the one of the example gate, it used the there are some coordination and there is background on the robotic stuff on the background, but control system it's I will explain. But you can see that it's here. There's some leg face difference between each legs, and it's undulate its body and create some kind of centipede type locomotion. So here we use the control algorithms. We use the Hildebrand gate parameters. This is the method used developed by Hildebrand for four-legged systems, four-legged animals. But we extend this method to the multi-legged systems. And one of our papers is now is under review in Bioinspiration and Biomimetics journal. It's gonna explain how we did this extension to the multi-legged system from four-legged to multi-legged system. But basically, here there are 2 parameters. The one is the leg phase shift. The phase shift between the legs on the same side and the consecutive the same on the same side, and duty factor, how much the legs spend time on the ground. So using these 2 parameters, you can define a lot of gates, and I can show the example. For example, this one used the leg phase shift to 50%. So it means that the diagonal legs are on the ground at the same time. And of course there's a body undulation, and here is a leg face is 90%. You can see it's how the difference between the 2 gates are. So if it's the leg face increase, it's more like an undulation and more like a animal like, but on the one this is more look like a tripod gate. So and of course, we can calculate how the displacement of the per cycle is changed with the leg phase shift. And we did some numeric analysis and experimental analysis on the right. You can see that all of them is for leg phase shift from 10 to 90. It's the experimental results are matched with the simulation. And what else? These are the until now is all the things in the robot. They are rigid, but as I said at the beginning of the centipede video, the animal video, I showed that the animal bends its body or its legs to adapt to environment. So here I find a way to apply this to the robotic robot. So here is it's a directional flexible leg. It's bent when it hits the obstacle. It's from the one side, but on the other side it's rigid. And also I add some soft joints to the robot here and here. This one's you can't see, but this one's seeable. So this helps the robot to adapt to environment. I will show the video of that. But first, I want to show how the flexible leg affects the locomotion. These are the 2 videos. It's the one on the left used only rigid legs, but you can see that after the first, first I need to explain the experimental setup. This setup has some roughness on the surface. We put the cubic obstacles, and it has a different height obstacles. You can see from the side video how it's the roughness of the surface is changing during the platform, walking on the platform. So the video on the left shows the robots that with a rigid leg without any flexibility, and it's stuck in the first cycle. But when we add the flexible legs, you can see, and also you can see from the top how it's behave like. The robot use the same gait. Everything is same on the left and right, but it can move in this in platform using this flexible legs without any sensing anything, just a passive flexibility. It's when it hits the obstacle, it bends back, and when it's past the obstacle, it turns to its original shape. With that one, it's without any control, as said, anything, any sensing. It improves the locomotion. Here, the results from different type of gaits with the different leg phase shift from 10 to 90%, and you can see that flexible legs are mostly better than the rigid. Rigid legs actually it's a bit robot with rigid leg just stuck in first cycle, or maybe just can go one cycle. But with flexible legs it can go, and it's also you can see it's the displacement is it's kind of similar for different type of gaits. This means that here in the top image you can see that when the legs bend, it's increased the contact area of the leg. So this makes the robot more stable. Of course, the robot has, since it has the multiple legs, it's also stable because of the multiple legs. But this also, the flexibility of the legs also increases the stability of the robot. The gait, you can see displacement is a little bit lower at the extreme cases, extreme leg phase shift, because in that cases the body undulates too much. And the robot can, because of the undulation, cannot move effectively. And the second one is the here is shows this video shows how the soft segments behave. You can see on the left, the robot doesn't have any soft segments, and try to go to the from the down, go down to from the stairs and go up to from incline with a 40-degree, but it can't do that. But if you add some flexible segments, again, these are the not controlled, these are just flexible passive segments. You can see it how it adapts its shape to the environment, and can climb the incline without any sensing any change in the gait. So this also helps. We also tested different type of we did multiple experiments and see that the robot with soft segments is better than the robot with rigid segment. Of course, these are the laboratory experiments, but we did some experiments on outside. Here there's a stick. You can see initially it's stuck, but with the flexible leg it's passed. It can also move. Yeah, actually, compared to other legged robots in literature, this robot is very small compared to the obstacles in natural environment, but it can move effectively there. And also, you can see how the flexible segments helps the robot go down from the stairs, which the height of the stairs are almost the same height as the robots. So. This is the part of the my talk is to explain how these multi-legged systems, flexibility on the soft materials on the body of the robot. And now I want to switch to the collective robots or swarm robots. Here, using the idea, as you know, from the previous study, multi-legged robot is good, and it's stable, more stable. It can move in many environments. Here I got an idea of how we can use the segments of these robots and create a small four-legged robots in an environment and do some swarm tasks, such as try to move the object in rotating. But when the environment is hard or task is hard, they can combine together and form a longer and powerful, more stronger robot and pass these obstacles or do the task. So here our biological idea is the ants. As you know, ants they are social animals. They can collectively move objects, such as in this figure, you can see that, sorry, I forgot to add the citation for the paper. This is one of the paper, not I wrote, but it's from literature, but I forgot to put the citation. So here is the many ants try to move the circular object, or they can also form some structures, such as here. They can form a bridge and pass this kind of gaps and obstacles collectively, in a creative way. So here the idea is using the similar idea in robotics, how we can improve the performance of our robotic system. So swarm robotics is maybe you know this, basically is the individuals in the system are autonomous robots, and the individuals are simple in physical design or in control and everything, but they can do some things collectively, and the behavior at the end is emerged from the collective dynamics. So there are local sensing and communication, but no centralized control or global knowledge of the environment. Just the robots knows the things that going around their close vicinity, and perform some behaviors just looking to their neighbors. So, as you know, there are a lot of swarm robots in aquatic and aerial environments. This is one of the examples from literature. These robots, the aerial robots, trying to do some, here, for example, they are trying to form a structure and do some tasks together. But in air, it's it's a little bit, maybe I can switch and it's a lot of things. So something like that. They can form a shape or something. But in air or in water, this is another example. The fish robots are forming. Let's see. This is maybe this one. So they form they behave just looking to their neighbors and do some collective behaviors. In air or in water, the environment are mostly known or predictable. You can say it's a very smooth environment. You don't have any obstacles and anything, and it's hard, but it still is easier than the systems. To control the systems easier than the one in terrestrial ones. There are a lot of terrestrial swarm robots. This is one of the example. The researchers from Harvard developed this Kilobots. There's thousands of the very small three-legged robots move on smooth surfaces. They can form shapes and other stuff, but they can't do any tasks such as to move the object, or it's because they are very small, and they just because of their legged system designs, they just move on smooth surfaces. Or other robotic system, again, these are the wheeled robots. They can move in smooth surfaces, but they can form a structure on the. You can see here is a legged structure. They can combine. It's a modular robots. They can combine together and form a legged robot. But this is also still in very smooth surfaces. It's not effective. There are few studies that use the legged systems, wheel systems on moderate rough terrain. It works very well in a smooth surface like that, but it's a little bit rough terrain is also working, but they are still limited to the work in laboratory condition or smooth surfaces. So here, this is our studies published in Science Robotics. Here the idea is, I think this is the first study that used the legged robots as a swarm. The individuals are legged robots and do some swarm tasks. As you know, legged robots are good at locomotion on rough terrain. They are because they have the discrete point contact, and compared to wheeled and other robots, it's legged robots are more adaptable to the environment, and they can move in many surfaces. So here, as I said, let me run the video. The robot, the unit of the robot is a four-legged robot that combines the centipede robot, that's two segments of the centipede robot, and walk with a diagonal gait. Here is the one example, an outside example. The single robot moving on leaves, and as I said, it's a little. The size of the robot is very small compared to the obstacles, and this is the components of the robot. Oops, sorry. Yes. So here the robot has 4 legs and controller. It's an Arduino type controller. It has a battery. Everything is on board, and it has 6 servos. 4 legs to control the legs motion up and down and far and out, and 1 for body and 1 for tail, the connected state of the tail. So and it's gonna show in the video more clearly from the top view. The servos are here. It's battery and controller located on the middle, center of the mess of the robot, and the robot has the similar leg structure, the flexible directional flexible leg, and also we need to add the passive similar to the legs. We need to add some passive tail to the back, because four-legged system, if you use a diagonal gait, 2 legs on the ground at the same time, it is not stable. It's flip over, and the tail helps the robot to move on many surfaces stably. Sorry, I made a mistake with that video. So here it shows how the robot moves on carpet without tail and with tail. Without tail, it can't move, but with tail, it can move on this surface and on other surfaces. And this is one of the example video that shows the robot to move on grass, mulch. These are the very rough terrain, actually, leaves and acorns. And the size of for example, the acorns is about 1 centimeter, and robot height is about 15 centimeter. So the size also very big. The obstacle size are very big. So as I said, the single robots are good, but it may not be powerful, stronger for some tasks, or it may not pass the obstacles individually. So here I designed a connection mechanisms and the tail. When it's a magnetic, the polarity change with the servo, and you can see in the video here when the tail is down, they disconnect. When the tail is up, they connect together, and these are the experiments, 3 different experiments that shows the single and connected robots performance. The one on the top, on left top, is there is a gap. I changed it. I can send the paper if you want, but here I think it's a 5 centimeter gap, and I changed this distance, the gap distance from 5 to 12, I think, as far as I remember. So and the robot tried to pass this gap, but single robot is mostly fell down because it's the center of mass is fell down when the legs are front legs on just stuck in the gap. But the two connected robots, you can see here, it can pass the obstacle gap easily because the center of mass is distributed and it can't fall down. And single robot here in the second one try to climb the stairs. The height of the stairs are 2.5 centimeter, and it can't. It's because the tail stuck or the leg stuck and it turns and it couldn't move. But when the 3 of the robots are connected, it's more stable. The legs most of the legs are on the touching the ground, and it's more stable, and it can't climb the stairs. And also I test this with the small rough terrain. There are obstacles, small wooden blocks. Still the single robot just stuck because tail or the legs are stuck there, but the multiple robots can pass. This is one of the experiments that shows how they behave as a group. So so here it's try to two robots try to move the object from the is a kind of big object they attach to that one, similar to the ants, and from Rotor into the target. There's a light source on the right. Actually, maybe I should also explain how their sensing mechanisms work. There are light sensors and touch sensor on the back, and light sensors on the front on each robot. The light sensor detects the light of the environment. Here, the task is to move the object to the target, which is the light source. And the touch sensors detect the robots if they are connected or not. If they are connected, they stop, all of the robots stop, and then they reset their gates and try to walk together. So here is two robots trying to do that, but they are not strong. But when we connected two of them to the each of them, it's a longer and stronger robots can pass the obstacles and move the object. One of them, for this robot is gonna detect the lights and gonna detach after it's detect the light. You can see here it's yeah, now it's the light, it's and detach and it's removed. So again, the idea here is to use this type of robots in natural environment, especially, for example, on the agricultural purposes, where there is this type of small robots to the farm, and putting some extra sensors, for example, sensors on the food to detect the humidity of the ground, the soil, or maybe other type of sensors that detect the nutrients in the soil. You can release this type of robots to the farm, and you can collect data. The future applications can be used in natural environment. Here is a 2 video. It shows the 4 different robots try move on environment, and here is a 3 of them. It's connected and try to pass the leaves. So as I said, these are just the tasks I did during my the experiments I did for the paper. But there are more of them. I showed just a few of them in paper. You can reach more of them. I can send the things. So this is my end of my talk. Thanks for listening. And if you have any questions, anything, I am happy to answer it.
Thank you, Dr. Yasemin. It was a very interesting presentation. I have one question. Your robot is based on servos. Now, have you thought of replacing or substituting the servos by artificial muscles so that it can be more lightweight?
So yeah, if I understand correctly, you are asking now is the robots are 3D printed if you use some soft actuators or soft muscles to do that. Yeah, it is possible. The only problem, I haven't mentioned that with the soft robots, they usually actuated with pneumatic systems, pneumatic actuation. It is mostly bulky and heavy. Yeah, you can't. It is now with the current technology, it's a little bit hard to design an autonomous robot that carry its own actuation system together. Normally, the soft robots, as you said, the muscles are very light, but the actuation boards and other stuff on the back is very heavy. So this is one of the problem that we can actually, if we a little bit time, maybe if I can show the. Let me show another thing. This is the. Can you still see my screen? Yeah.
Yes.
So you remember that at the beginning I showed that the earthworm robot that used the soft silicone actuator mechanism. Let me, yeah. So I couldn't. I will pass all the biological part, but here the robot has the very soft body, and as you said, is lightweight. But there's maybe you can see that there are tubes coming from and a huge control board and on the back. Yes, it is very lightweight, very easy to control. Here, for example, I am gonna show the just the simple tip bending here, not bends, but this robot can bend its tip to left to right, and it can move in heterogeneous environment or in tube. And also, let me show one more video here. Again, it's using the just bends its tip left to right. It can move in in a pipe. It can climb in a pipe very easily without any sensing anything. So. Yes, you are right. It is a very easy to control, but the application is a little bit hard for autonomous system. But 3D printed robots are very easy to design or build, and the rigid motors are very predictable, easy to control. So now I'm thinking about mostly is the combining soft and rigid parts in a body. It's a kind of more efficient for the real world application. Of course, maybe in the future, some new materials or new actuation systems or new devices can be developed. It can be we can also use the soft materials to design legged robots and other type of robots. So yeah, this is another study, but I want to mention the swarm part, not this one. Okay.
Thank you very much.
Yeah, you are welcome.
A few more questions from the audience.
Okay.
One by one. Aniruddha, please.
Thank you, Professor, for that talk.
You are welcome. You are welcome.
Yeah. So I just have one question that when the robots are actually moving, the legs generally tend to go out of phase, like when the external forces are acting on the legs. So is the mechanism able to like adjust the phase so that while it is moving, it again comes back to phase while it is crawling?
So let me go to this slides. You are asking the, let's see. Oops, not this one, sorry. Here. You are asking this leg phase shift,
yes.
I think. Yes. So, and these are the open loop gates, actually. It just controls the phase of the legs and the undulation of the body. Doesn't have any sensor from the tip of the robot, tip of the foot, anything. It doesn't send anything. Here, the leg phase shift is, as I said, is the difference between the leg, phase difference between the legs on the same side, the same adjacent legs. So this is the very simple, you just control the footfall pattern, actually, not anything else, just how the foots are on the ground and the time they spend on the ground. These are the two parameters, and with these two parameters, you can create a different type of gates. Here, such as you can see, it's a 90% means the legs are after the one cycle, 10% of the cycle, the other legs on the adjacent legs on the ground, and it's continue to go to the from head to tail. So these two parameters are enough actually to control legged robots. Also, it's also useful. Our latest paper is going to be published soon. So it's also useful for legless systems such as snake type robot. You can control these patterns. How this maybe you know the sidewinder snake, it's goes the side way, and the point of contact on the body is changing like legs on the ground. So you can control how the point of contact points of change during the time, along the body with this method. It's a very simple, very efficient. Of course, there are some geometric, we call the geometric mechanics. There is a theory, physics theory on the back, but without any knowledge from the ground or anything, you can control this type of simple robots. But if something happens, for example, if the obstacle in front of the robot, it couldn't pass, maybe if it's a big obstacle, then this since you don't have any sensing and anything, you just stuck. These are work with the mostly is if the size of the obstacles around small, the robot can pass the obstacles. In that environment, the system, this method is work. But if you want to do some more complex stuff, if you want to include the sensing from the environment, you can, of course, you can change the heading of the robot with the sensing and create a different type of kits. But these are not presented in this study.
Thank you, Professor.
Yeah, you're welcome.
Yeah. Hello.
Yeah.
Yeah, Professor, thank you for your nice presentation.
You're welcome.
Yeah, I'm having one question regarding to the mechanism, what kind of mechanism you have used to move the legs? Means, is it a 4-bar or some sort of other?
Yeah, it's a kind of 4-bar. Let me let's go this video, and you can see here. Make it a little bit bigger. This leg has a return spring, and this leg connected rigidly. There's a joint here, and this is a rigid joint, and it's connected to the servo, this mid servo, that control the up and down motion of the robot legs. So here you can see better. It's a kind of 4-bar mechanism. Yeah, you are right.
So it seems to be that it is just this motor is connected in between with the 4-bar. So means it is like a dual pole of 4-bar kind of mechanism, it seems.
Yes, yes, you are right. Maybe dual. Yeah, it's maybe made better words. And it controls. You can see this how this one is up, the other one is down. Actually, in my paper, the paper is published in 2020. I think it's in Robosoft, one of the conference paper. But it's a very, I think, it's a very nice. You can take a look at that. I used the flexible connection, not the rigid one, in that between the servo and this leg. There is a Kevlar thread on between this point. This one helps the robot to. Because in that system, if the legs are rigidly connected, it's if one of them is on the up, it's push. Other one is push ground and apply force. But if the connection between the motor and the legs are flexible, this one is on up, doesn't affect anything about this leg. So you can. I'm also working on in my lab, in my group now, is how the flexibility of the robot part, or how the flexibility of the legs or body or shell of the system of the robots helps the legged locomotion. So this is one of my now current project. I'm also working on writing a proposal, grant proposal about that, apply all the flexibilities and investigate how they affect the locomotion.
My second question is regarding to the type of control strategy which you have used in this locomotion. What kind of control strategy?
Yeah, so as I said, it's open loop control. You just send the position of the servos at each time step. So there's a cycle. For example, one cycle in that long robot is the cycle is start with the first leg on the ground and go to the end of the robot. This is a one cycle. And you can control in a cycle, you can control which time point, which servo or which legs are on the ground or in air, or the angle of the servos, leg servos or body angles in each time step. So you define one cycle and define all the points, the position of the servos in that cycle, and apply this as an open loop. So it continues to do this cycle n times, depending on the number of the cycles you want. So it's very very simple, actually very simple. but you need to think about, as I said, the Hildebrand method is, for example, we find it's very useful. Normally, people use it for four-legged systems, but it works for the multi-legged system too. So you can see the paper.
So it's simply a position control, not of
position. Position control. Just
feedback loop is there is no feedback loop.
No feedback, just the position control. But you can add feedback, of course, as I said, from environment. You can add some cameras or some other feedback and change the gate according to that.
So
we have a lot of gates that, for example, the diagonal gate, the 50%. Let me video also. This one, for example, is very good at on surfaces that is smooth. So you can use this, for example, if you can detect the surface properties, you can use this gate. But if it is maybe is a slippery surface or something, you can use the other gate. You can switch between the gates. But we are not controlling each leg in a time with sensing. We are not controlling every positions in a closed loop system. Just the open loop.
So there is one of my one thought I have regarding to this, that if we can we use some sort of contact sensors which can be used to make a feedback loop, and
yes, definitely. You can use very simple. Maybe you can just use the limit switches. You can put the limit switch to all the legs and see which leg is on ground or not. You can control that. It's also be feasible. It's maybe helpful for rough terrain, and you can detect which legs on the ground, touching the ground, and depending on that, you can change the. Actually, animal is. If you take a look at this video carefully. Animal gates are on rough terrains. Here is in smooth terrains, clear. There's a wave and legs are touching, and you can see the legs are creating a virtual legs. The multiple legs can combine. It's very you can see the everything easily. But on rough terrain, it's animal. The legs are randomly. It seems more randomly touching because the surface is not smooth. We can use the flexible legs in the robot is help to increase the point of contact of the legs. It's also a little kind of similar to the animal, but of course, if you add some sensors, the touch sensors and other stuff, it more look like an animal how they control their locomotion in rough terrain.
Thank you, Professor, for your work is really very innovative. That's really cutting edge.
You're welcome. You're welcome.
I will request Somnath for his question.
I can't hear.
Thank you, Professor, for your excellent talk.
You're welcome.
I actually learned a lot after listening your talk. So I have a question regarding to swarm robotic perspective. What kind of simulation environment do you use? We all know that Elon Musk OpenAI already released all libraries and APIs 2016 onwards, totally open source. So what kind of simulation you used for swarm robotics in multi-agent environment?
Yeah, this is a good question. Actually, I haven't worked on any simulation stuff for the swarms. But I'm planning to do that. So far, I just work on the experiment. I am experimentalist. Experimentally, I build the robots and do the experiments and see the results. But now I write another proposal. So it's about how the swarm of the legged robots move the objects collectively. This will be included some simulation. Actually, I haven't used any, but I will learn in the future. Hope maybe maybe in the future you can contact me. We can do. We can chat later. But now I can't give any answer to this question. Of course, there are a lot of swarm algorithms used for, especially for the aerial and the robots that move in fluid. But for the terrestrial systems, such as this type of rotary, not a smooth one. I believe there isn't any simulation. Yeah, there isn't any simulation yet, because there are some. Yeah, I know as I showed the Harvard study, there's the Kilobots, the small thousands of robots. They do some pattern shape. They form a shape patterns of the different type of patterns. They have some. They explain that I don't remember the exact name of their algorithm, but they use some algorithms to make this type of system. But as I said, it's a very it's maybe helpful for some reason, building a shape or doing some. But I think in real world, is the swarm of robots should do some tasks, some real tasks, not other than the creating a shape or something. So they need to move objects. Maybe they need to do some tasks together, push the object, for example, or modify the object together. So, but as I said, as far as I know, there isn't any simulation or something that can work on real rotary environments for the swarms.
Thank you so much. You've already done a lot of innovative work that we see. So I really appreciate
please feel free to send email if you have any questions, and if you can't reach the papers, you can search my name and in Google Scholar. You can find all of the papers recent ones.
Sure. Thank you. Thank you so much.
Oh, you're welcome. And thanks so much for inviting me to your symposium. It was inspiring. It's a little bit early in my time. Sorry, I couldn't attend all of them, but the part I attended this week on Monday we organized a workshop in RoboSoft conference. Maybe you heard about it. IEEE on soft robotics. And so we also organized a workshop in borrowing soft robots. It's more maybe agricultural approaches. It's more applicable. Maybe in the future, we can talk about that too. It's a soft robots application in borrowing that can investigate soil and do something. It's a very challenging topic. A lot of speakers say that I believe in the pipe locomotion in confined environment, also challenging in a pipe, such as the one last speaker that showed. It's this softness flexible to help the robots to move this kind of confined environment. But burrowing is harder than this locomotion in pipes and other stuff. So I'm also working on that. Maybe in the future, we can talk about that.
So one
You're
last
welcome.
question can we take from Mahendra? One last question.
Hello, Professor Yasemin.
Yeah.
Mahendra. My question is that in that this multi-agent, in swarm robotics, if there are multiple robots, that is there any central intelligent robot, or they do work in simple basic senses only?
Yes. So the swarm robot. Normally, the swarm robots should be decentralized. There shouldn't be any the mechanism that control all the systems. But actually, in most of the study in swarm robots mostly have the centralized system. They control, for example, they mostly done in laboratory environment, and they have a controller on top of the camera system. They can know where all the robots are and send the signals from central. So this type. There are few studies that work on the decentralized. My one is the decentralized one. The robots are just detect the other robot when it's connected. There's only one sensor, or if there's a light or something coming from the other robot, it can detect as another sensing. But other than that, there isn't any central controller that sends signals to the robot to, for example, go there, or other robot go there. So there are studies, as you said, but my studies that doesn't have any centralized control unit. Okay. But for example, the Harvard robots, the 1,000 robots, they say that it's kind of decentralized. The robots just knows the robots in the neighborhood, but they have still a controller on the central controller. If you can read their paper, they sent us the position of each. They know it knows the position of each robot and sends the signal to each one to go next to the other one. So it's a kind of centralized control. But the swarm in nature also, in swarms, for example, birds, they fly, they don't have any central controller. They just detect their neighborhoods and adjust their speed or direction heading according to that. And it's at the end, it creates an emergent, very beautiful behavior at the end. Yeah, people working on to understand the mechanism, the model, they try to model this behavior, but it's maybe you can simulate some behaviors in individual. You can change the individual behavior and see what's going on at the end. But now they don't know if you give the overall behavior, what should be the individuals, what should they do? This connection is not, they can go from this side to the other side, but can't go from the big, reverse is hard. I believe a lot of people is working on that, but it's still they still try to understand what the emergent behavior, if we give some behavior to the robots, what should they do individually to reach this point. So yeah, it's I think the swarm robotics is a very very amazing area. You can both in biology and in robotics and biology also. It's both of them is amazing. So I will continue in Notre Dame. I will continue to work on the swarms, different type of swarms. Hopefully, it's gonna be more more study, more research will be done soon.
Thank you, Professor Yasemin. It was very interesting. But your work was very interesting. Thank you.
You're welcome. You're welcome.
Thank you, Professor Yasemin, once again.
You're welcome. You're welcome. Sorry, as I said, I couldn't attend to all the conference, but hopefully tomorrow maybe I can also join to some of them. Thank you so much for inviting me. And as I said, feel free to send emails and anything if you have any questions, further questions.
So can you please send the name of that conference in the comment chat box so that we can see that conference name?
Robosoft? Let me.
Yeah,
let me, if I can stop share, I think. Yeah, it was this week. Actually, I think it's for online speed. Online, you can freely join. Hopefully, if we do our meetings last week, I can inform you. But it's a Robosoft. Yeah, this is a very nice community. You can this year is the Robosoft 2022, but you can maybe join the next year. It's kind of, I think maybe next year it's gonna be some part of it's gonna be online, so you can join freely. And a lot of there were a lot of study that use the pipe inspection or some stuff, using soft robots or manipulation, soft manipulators. I think yesterday, tomorrow's talks about some manipulation stuff, and so Robosoft conference is also. They have a lot of manipulation studies, soft manipulators.
Thank you.
Okay, you're welcome. I think it's the end of your today symposium.
We still have 2 more talks after 1 hour break.
Okay.
One from Carnegie Mellon and one from our group. So
okay.
2 more talks after about an hour or so. That will be for today. We will be very happy to have some collaboration with you because as the last speaker before you have shown, Kanai have shown that we have a pipe health monitoring robot for these things. So we would like to develop different other kinds of robots also for pipe crawling and such things. So we will be in touch with you.
We can keep in touch and we can talk about things later if you want.
Yeah.
I am happy to talk about that. Yeah. Okay.
Okay, so let us thank Professor Yasemin once again.
Okay.
Yeah.
Thank you very much, Professor. Thank you very much.
You are welcome. You are welcome.